Right, because this is joules and this is kilojoules. So I divide it by 1,000. If I want this at, what did I say, 450? Now I've got delta G0 at 450. And if I want to calculate delta, the K at 450, I have to recalculate delta G0. Question? She doesn't know the answer, ask me.
No, I was just asking about the previous step that you did where you removed them. Where you
Oh, this
explained
one
why,
right
yeah,
here,
didn't
I'm
just
explaining
explain.
units, yeah.
Oh,
I was just showing you because somebody said, because they looked in the table and it says, this number is 205 joules per mole per K.
oh, okay.
And I said, the answer to this problem is, wherever I wrote it, 296 joules per K, there's no mole in there. That's because each one of these you have to multiply by the coefficients in the balanced equation. I didn't put it in because they were all ones, but don't forget to put it in if they're not ones. Okay. Then coming back to this, if I have all the data in the world, the easiest way to get the delta H at a higher temperature, or the equilibrium constant at a higher temperature, is just to remember, we're assuming these don't change, but delta G changes as you change the temperature because it's part of the formula. Bigger number here makes this term more important. That was that little table we looked at the last time. A smaller number for T makes this number less important, this number more important. Okay? So if you have all the data, this is what you would do. Now, one of the problems I like to give, I only give you delta H's. Again, you're assuming it doesn't change temperature. When I say K at 298, and you want to calculate K at 450, you say, how the heck can I do that? And I will tell you. Okay? And when last semester, when we did vapor pressures of liquids, we talked about the Clausius-Clapeyron equation, and I said to my students, if you're not coming back to 1B, make sure you look at the Clausius-Clapeyron equation and study it and know how to use it. And I said, I'm not going to worry about it till I get to 1B, because I'm going to do it all together at one time and give you the reason it works. Anybody took 1A from one of the other instructors and knows what the Clausius-Clapeyron equation is? This is the vapor pressure. That's the Clausius-Clapeyron equation. You know the vapor pressure at one temperature and the enthalpy of vaporization. I should put a V for vaporization here. You can calculate the vapor pressure at another temperature. We saw this equation. I'll just spell it so you can spell it. Arrhenius equation, when we were doing kinetics. And it said, now these are the rate constants for the reaction. Those two equations look the same. And if you read the rest of this chapter here, physical chemist, these are the equilibrium constants. Equals I say, fantastic, all those equations look the same. Why does it work? I'll tell you now. That's why I didn't want to do it way back then, because anybody can plug numbers into the equation and get an answer. Notice over here, I gave you K at 298, I gave you delta H. You know the temperatures, you know the delta H. You know what R is, right? You have to be consistent with units. If you use 8.314, then delta H has to be expressed in joules. Okay? But that's easy to do. Why does that work? I said it a few minutes ago, it's right there. I wrote 298 here, I could have said T1, but I said 298. The only reason is because if we look up data in tables, we can calculate delta H of 298, but let me just call it T1. And I justified it by talking about liquid going to gas, and no matter what temperature we did it, even though the absolute entropies for each substance increased, the entropy difference between the reactants and the products didn't change much. So that's all I'm saying again. Then I can say, what? That's a delta is equal to, by the way, this is the answer you have to know, and I'm just showing you why that answer works very briefly. I'm going to solve this for T1, and I'm going to get rid of this part, I don't need that, and I'm going to solve it for delta S at T1. And it's going to be equal to, bringing this over here, delta H0, right? And I brought this over here, plus R. I have to put this over T, by the way, because there's a T in here, so I'm dividing by T1. I divide this one by T1 and it's gone. K1. Okay? Everybody's happy with my algebra? Good. Then I'm going to write and again, the assumption is delta H doesn't change much with temperature either. Since I said delta S at these two temperatures are going to be about the same number, I'm going to equate these things. Delta H0 over T1 plus R ln K1 equals delta H0 over T2 plus R ln K2 and now I'm going to put all this together on one side. And then I'm going to divide through by R, and then I'm going to say ln K2 minus ln K1 must be K1. Okay? How about that? That's what I wrote here. Except you said, no, you had one here, two here. But notice I had the T1s and T2s reversed. And the reason all these equations have exactly the same format, even though they're calculating different things, is because the processes that they're talking about have the same entropy change regardless of the temperature. And there we are, I'm done. This is what you need to do to solve the problem, and each of these is exactly the same thing. We mentioned this when we went through Arrhenius And I said the same thing when we went through the Arrhenius equation, kinetics. I'll talk about it when we get to thermodynamics, because I didn't want to talk about Clausius-Clapeyron last year, because I wanted to wait till I got to thermodynamics, and then I can tell you why it worked, which I just did. Now I'm done with all the things we can say about temperature effects, and I'm gonna just about be done talking. When we get to electrochemistry, we have to talk about a chemical system. What chemical system are we gonna be talking about? Oxidation reduction. The electrons are moving from one place to the other. Instead of having them go from one reagent to the other, we separate the reagents and make the electrons go through a wire to get to the other one. So you have to know what? Redox. Now's the time to go back and look at that redox chapter. But now it's time for the exam.